PCR diagnostics for infectious disease. Most believe that because infectious diseases are less common in developed countries than developing countries, they don't pose a threat. But this is quite the opposite. Infectious diseases are the second leading cause of death worldwide. We can date the first infectious disease all the way back to the plague of Athens in 430 BC, to COVID-19 in 2019, to present-day influenza virus that is adapting and mutating every year. We humans have always experienced some form of infectious disease. Now, one of the issues that countries had when dealing with infectious diseases is not having rapid diagnostics for early detection. Previously, hospitals had struggled using traditionally slow culture-based assays that either were not sensitive enough when patients were prescribed antibiotics, or they weren't even able to culture certain pathogens. Now, the question is, how did scientists overcome this massive hurdle? Well, they used molecular testing called PCR, also known as polymerase chain reaction. Now, traditional culture-based methods relied on phenotypic traits. PCR, on the other hand, uses sequence-based hybridization, giving a greater specificity when identifying pathogens. PCR also eliminates the need to cultivate any pathogens. This allows scientists to get more accurate and more specific diagnoses to their patients. Now, PCR is a technique used to amplify a segment of DNA, and it uses a DNA sample as a template for this replication to occur. PCR involves 3 steps: denaturation, where the sample is heated, causing the double-stranded DNA to separate in 2 single strands; annealing, allowing short DNA primers to bind to complementary sequences on the DNA; and elongation, where DNA polymerase synthesizes new DNA strands by adding nucleotides to the primers, extending the sequence. The DNA generated from the replication is itself used as a template for further replication, generating millions of copies of DNA in a short time span. Scientists have come up with an even more specific PCR called real-time PCR, which allows for the measurement of products simultaneously with DNA amplification, eliminating the visualization step in regular PCR. It requires a fluorescent-labeled DNA probe which specifically anneals to that target amplification sequence. The probe emits a fluorescent signal in the presence of the target sequence, with the intensity increasing in proportion to the amplified product generated. The probe is labeled with 2 different fluorescent dyes. On the 5' terminus is a reporter dye, and on the 3' terminus is a quenching dye. This probe sequence is homologous to the internal target sequence present in the DNA. When the probe is intact, the 2 fluorescent dyes are close together, resulting in a quenching of the reporter dye emission by the quencher dye, resulting in no signal. In the elongation phase, the probe is cleaved by Taq polymerase, releasing the reporter from the quencher and allowing the reporter to emit a signal that's detected and quantified. The amount of reporter dye signal measured is proportional to the amount of PCR product made. Now, results are typically displayed as amplification plots, resulting from a series of fluorescence measurements taken at defined time points during the amplification process. Now let's apply this to the detection of Mycobacterium tuberculosis. The primers and probes are selected for the gene sequence encoding the 141 base pair region, also known as the IS611, a conserved region. Now, this sequence is unique to Mycobacterium tuberculosis complex, differentiating it from other bacteria. Now, the process is the exact same as before. Instead, we use a probe labeled with 6-fan that emits a blue light attached to the 5' end and the MGB quencher linked to the 3' end. Now, if we detect a strong presence of this blue fluorescent signal, we can almost confidently diagnose the patient with M. tuberculosis. This allows for a fast and accurate diagnosis from the doctor to the patient. Today, PCR is an up-and-coming method for identifying pathogens compared to culture-based techniques that were just insufficient. However, there's been a limited effort in applying PCR into hospital settings where time is of the essence. As we strive for advancements in more accurate and efficient testing, there's been a pressing need for increased funding and research regarding PCR and its applications in infectious disease, especially in developing countries where infectious disease is the leading cause of death.